Now, another concept is basically the horizontal shear transfer. Why is it important? Now, if you see here, when the deck and girder acts together, if there is going to be a slip, then you are going to have this kind of deformation that it is possible. If the interface is not good, then you are going to have slip that is happening at the interface that is going to create non-composite action. So, these kind of shear stresses are going to develop at the interfaces that we need to design for that by providing some adequate shear reinforcements across that interface. Okay, now let us look at how do we do that. These are the cases where we have talked about for precast elements are being used. On top of that, we provide all those cast in place slabs to provide the diaphragm action or to provide the continuity. In order to achieve the complete composite action, we need to have a broad contact surface, and roughening the top surface will ensure composite behavior, right. So, this kind of different surface profiles will be created. The rougher the surface it is, the better it is for composite action, because the shear transfer will be better. So, you can see if the surface is very smooth, then your shear transfer will be less, right. So, for composite section having less contact surface, the vertical stirrups are usually provided. Okay. So, you provide this kind of vertical stirrups, and that will ensure the monolithic action. So, like this, we try to provide the vertical stirrups and extend it through that and pour the top slab. So, that is going to create prevent the slip, and it will ensure that proper shear stress is getting transferred at the interface. Okay, now what the code says for an elastic uncracked beam, we know the horizontal shear stress due to bending is VQ by BI, right. B is typically the width of your web, right. Now, the code gives you different values that we can consider for the horizontal shear stress at the interface. For example, if I do not have any links, that means no stirrups between the precast element and the deck slab. If the slab is just as cast or extruded, I take for different concrete strength, code gives you value 0.4 megapascal, 0.65 megapascal. If it is also it's brushed and it's also washed to remove latents, and then if you are treating with a retarder or cleaned surface, then you get slightly higher value 0.7 megapascal for M25, for M40 and above we take 0.8. For same all the three conditions, you see when you provide links, your horizontal shear stress what you can transfer becomes higher. For example, if you see without links for M40 for the first case 0.8, the moment I provide some nominal links, then my limit 0.8 becomes 2.5, higher the limit. So, higher the vertical stirrup that we provide, the horizontal shear stress what I can develop permitted by the code is also getting higher. Now, when the horizontal shear stress exceeds the values that are given in this code, typically we provide this stirrup requirements, area of the stirrup. Area of the stirrup is given by 1000 into B into tau h by 0.87 Fi, where tau h is the horizontal shear stress and B is the contact width and Fi is the characteristic strength of the stirrup reinforcement that what we are going to provide. Now, let us look at it. When the links are provided, again the cross section area should be at least 0.15% of the contact area. Just like in stirrup, in web shear, we provide minimum stirrups. Here also for horizontal shear, some minimum reinforcement is required. That minimum reinforcement is 0.15% of your contact area. And the links should be adequately, should be anchored on both sides. The spacing here, either it should be less than 600 millimeter or 4 times the thickness of your in situ concrete. For example, if your thickness of the slab is 100 mm, then my horizontal stirrups, so the stirrups should be provided at a minimum spacing of 400 mm. I cannot exceed more than 400 mm. That is what it is, right. So, these are the cases. Now, how do I calculate the contact width? For example, you have a T section and then you provide it. So, from here to here is your BI. If you are providing, let us say I have a web, then we provide only this width as your contact area, right, BI. So, like that, this is, for example, let us say you have contact area is, this is how you provide it. So, this is a old concrete element and you are providing a new concrete like this. So, this width you take it as BI. Similarly, between the joints between the wall panels, again some requirements for geometry has to be ensured. For example, this projection has to be less than or equal to 30 degree when these two elements are joined, and the distance between these projections also should satisfy the 10 times the D distances which are given in your code IRC 112/2000. Now, interface shear, as expected, always the demand has to be less than your resistance, and VEDI is the interface shear stress because that is coming from external load, and VRDI is the resistive capacity of the section. Now, what is VEDI? The resistance, the shear stress due to demand. This is shear force multiplied by beta divided by Z into BI. Now, what is VED? VED is your transverse shear force that is acting in the cross section. Z is your lever arm to resist the internal forces, and BI is the width of the interface, right. So, for flexure also you will have compression and tension. What are the distance between the compression and tension is your lever arm, and multiplied by BI is your contact area, that you divide that with respect to VED. So, then you get your shear stress, horizontal shear stress demand, and the resistance already that was given in the previous table that was given to you. Now, from shear friction theory, I can develop again resistance also, which is mu into sigma n, which is a normal stress that is acting between the two planes, and rho into FYD times mu sin alpha plus cos alpha, and which should be less than 0.5 times your VFCD. What is VFCD? This is your concrete shear capacity. So, whatever the shear friction force that we are resisting, that should be less than or equal to 0.5 VFCD. Okay. Now, what is alpha? Alpha is the angle of the reinforcement to the interface, and sigma n is a minimum coexisting normal stress, and it should be less than 0.6 times your concrete design compressive strength. Here also you see here FCD is your concrete strength. What is rho s? Rho is your reinforcement area, AS divided by AA. Now, what is AS? Area of the reinforcement that are crossing the joint, and A is the interface area, right. So, this is like a reinforcement index. Now, depending upon the different surface types, I can assume different friction coefficients. If I have very smooth surface, I have to assume friction coefficient of 0.5. If it is indented surfaces like this, okay, this kind of different indentation that I create purposefully between the precast joint, then I can go for a very high friction coefficient of 0.9. Okay. So, that will help you. This is coming from your shear friction theory. So, you can see that from the friction, it is always the shear transfer will be mu into sigma n, which is the normal stress. In addition to that, there is also some stress that will be transferred through the shear links that are connecting that interface. That is what the concept is. This is your transverse shear stress, because from the friction coefficient times the normal stress plus some reinforcement contribution. That is what we are looking at it. Okay. Now, again let us go through a quick example. For the same problem, let us design a suitable horizontal shear transfer reinforcement for composite section, and the span is 20 meter, and the precast beam is just extruded. That means, it has a smooth surface, right, extruded surface. FCK of the slab is 25, FCK of beam is 40, and ultimate strength is 1860, effective pre-stress is 1100, and your effective pre-stress is 2200 kilonewton, and area of pre-stressing is 3090 millimeter square. And these are the stresses that are going to develop, and we have to design for that. Let us say that I am using approximate method that is given in IS 1343. So, I go back and I know the area of steel. So, using the reinforcing index FP into AP by BD into FCK, I can use this table 11 and I can quickly calculate my neutral axis depth. and that works out to be 159 millimeters. So, if you don't want to use this approximate method, you can do the moment curvature analysis that we have discussed in the flexural chapter, and you can derive the entire moment curvature, and you can look at the ultimate moment and then calculate your compression and tension forces. This is a very simple way of doing it. So, the tension force, once you do XU by D, I can calculate my stresses as well, which works out to be 1860. My tension force is AP into FPU, which is working out to be 2585.4 kilonewton, and compression force is 0.446 FCK into B into XU. XU we have calculated it, which if you substitute that, you get compression force of 2500. Because it is an approximate method, that is the reason C is only approximately equal to tension. It is not exactly equal to tension. Okay. So, because this is coming from approximate method. Okay. So, that is the reason. So, but we are taking higher force tension force 2586, and then when you design it, what are the area of the interface, and you can see this is your BI, which is equal to 350, only the web width we are taking, right, and then that is happening over from support to the midspan. So, the maximum moment I am assuming that it is happening at the midspan. So, the entire interface is BI times L by 2, which is 10,000 by L by 2 is 10,000. So, if you substitute that, you get average shear stress is 0.73 megapascal, right. So, we are saying for maximum, then when you have to look at it, shear will be maximum at the support. So, I am going to take for design 2 times average, which is going to be higher. So, my shear stress for design becomes 1.47 megapascal. So, but we have seen from the previous thing, for precast beam without shear link, permissible stress is only 0.4 megapascal. My demand is 1.47. So, I cannot rely only on the concrete. I have to design the shear links. So, tau H is greater than tau permissible, because this is tau permissible, right. Shear reinforcement is required. So, you are going to use Fe415 grade, and I am assuming because the requirements are high, I am going to put 10 mm dia 2-legged stirrup, and AST is 157 millimeter square. So, if you substitute, AH works out to be for this shear stress of 1.47, B is 350. If you substitute, I get 1432 millimeter square for every 1 meter. So, that again spacing is calculated by 1000 by AST times AH, which works out to be 109.62 millimeters. So, that I have to provide 10 mm diameter stirrups at 100 mm center to center to satisfy this horizontal shear stress requirement. So, if you plot it, we have to be careful. So, if proper provision is made for horizontal shear transfer at the interface, then the entire section will be effective in resisting the flexure, right. So, this is the thing. So, this is the way that we did. Now, we are getting into the flexural strength. That means, at ultimate, how do we do the calculations? So, if I ensure that I have adequate vertical links that are connecting between the cast in place slab and the precast web, then the entire section we can say that it is going to resist the flexure at ultimate load, because now I have provided links that is not going to allow the horizontal slip, right. So, due to the bending of the precast beam prior to the casting of the inserted slab, typically there will be a discontinuity of the stress at the interface. So, right. So, because my stress strain curve for cast in situ slab and girder, I am assuming that cast in situ slab will be made with a lower strength concrete. Okay. This is a good assumption, because deck slab will be quite larger in volume. So, typically people tend to use low strength concrete, and also for placing the concrete you need higher water cement ratio or admixture dosage. So, typically you end to have lower strength concrete. So, it is a reasonable assumption, right. So, this is the section. So, if you look at it again at ultimate epsilon Cu, we take it as 0.0035 in India, and these are a strain from strain compatibility. Now, depending upon your neutral axis, now the web and the flange will contribute. But typically in a composite section at ultimate, if you ignore that strain discontinuity, because lot of redistribution of stresses also will happen. Now that is why the key is, if I provide adequate horizontal shear stress at transfer at interface, then that minor strain discontinuity can be ignored and I can assume a simple linear strain distribution, and you can do the analysis like a flanged section like what we did in lecture module, right. So complicated stress distribution, and below the interface you have precast elements, so you have a high stress strain curve. Above the interface you have low strength concrete, so stress strain curve will be different. So that is what we discussed previously. So in T sections, typically composite sections or T sections, and your neutral axis is usually within the interface, and the ultimate moment will be governed by the steel reinforcement, right. So if the neutral axis is going to fall outside the interface, it will be designed as a regular T beam, but typically in T section neutral axis will be within the interface, then you can design it will be governed only by the steel, and you can design it like a rectangular section. Then we have already discussed how to do the analysis of a T sections. You can refer to module 4.1, 4.2 and 4.3 for flexure, how to use strain compatibility for analyzing the T sections, and then you can calculate your ultimate strength very easily. So there is no problem, right. So let us quickly go through one example, and you can see the deck slab is having this is the same cross section 1400 by 200 and with a web thickness of 350 and 1500, and my slab is having 20 megapascal, my beam is having 40 megapascal strength, and ultimate strength for pre-stressing steel is 1860 as usual, and effective pre-stress I am taking a lower value of 1100, and effective pre-stress is 2200 kilonewton, and AP is 3090. Again we are going to use your table 11. I calculate this parameter reinforcing index WP, and that works out to be 0.061, and then use a table 11 and I get my stress as 0.87 FP, which is 1618 megapascal. Neutral axis depth is 0.13, so XU is 195 millimeter. Then I take the moment FPU into DAP, which is your tension force multiplied by the lever arm, which is Z D minus 0.42 XU. Then you get your moment resistance of 3189 kilonewton meter. This is for flexural strength, right. So this composite section, you can see it can have a very high moment strength of 3189 kilonewton meter. How do you do for shear and diagonal tension? The general concepts what we have mentioned in module 5.1 also apply to composite section. It is the web that is going to resist the predominantly shear, but at the same time the flanges also you have to put some reinforcement, stirrup reinforcement, horizontal stirrups have to be provided. And shear design is a factored load design. That means at the incipient, when it is going to damage, when you load it and all, it becomes irrelevant. So it is we are doing the analysis at ultimate. Again, a lot of stress redistributions will be there. So the entire composite section you can assume it to be resisting the ultimate shear. So the VC again is calculated based on the strength of the precast web beam, that is typically the web. So you can go ahead and look at the calculations. So this is for both flexure and shear for ultimate strength point of view. Now we also have stresses at serviceability limit state, that also we need to be careful, and we have to make sure that the permissible stresses, again it depends upon the compressive strength of precast and the cast in slip concrete. And British code it allows high compressive stress, typically up to 50% of the compressive strength, typically 50% higher than the normal, and higher stresses are allowed only if the failure is due to steel elongation. That means we want steel to always yield. See, if the yielding is dominating the behavior either in flexure or shear and not through concrete crushing before steel yielding, then you can permit higher stresses. That is what the BS code is saying. And flexural tensile stresses also in situ concrete at interface, there are some limits that are given, allowable flexural tensile stresses, especially in situ concrete at interface, you get 3.2, 3.6, 4.5. Higher the strength of the concrete, higher will be the flexural tensile stress that is allowed. And this will happen when you have transfer of pre-stress that are happening sometimes.